Hello everyone, my name's Yi. In the previous session, Yuanjun already gave a wonderful introduction to human activity understanding, including the input data, the common tasks, the popular methods, and the open challenges. In this session, I'm going to cover two things. One is to show you another perspective of recent video modeling progress in terms of time. The other is to introduce GluonCV video library, which is one of the most comprehensive and easy to use toolkits for video understanding tasks. After this session, you will have a more structured and complete picture of video modeling methods and learn the technical details in reproducing state-of-art approaches. Here is a quick overview, divided in two parts. In the first half, I will present a chronological review of recent video modeling methods using deep learning, starting from year 2014. Basically, the timeline starts from using single-stream network, then to the two-stream networks, and to the rise of 3D CNNs. I will also talk about other spatial temporal modeling methods. In the second half, I will introduce GluonCV video toolkit, including its comprehensive and reproducible model zoo, its flexible and customized usage, and detailed tutorials. I will also share some interesting observations during my reproducing experiments. Okay, so now let's do the chronological review first. Here is a timeline of recent milestones in video classification, particularly human action recognition, from the last 6 years. Despite most methods were developed for classification tasks, other video tasks like action detection, tracking, video imprinting also borrowed ideas directly from these methods. So it's really helpful and necessary to read these papers no matter which video-related task you are doing. If you're already in this field, you probably know most of this work already. But if you are new to this field and don't know what these short names stand for, you should be able to search it on Google with a short name followed by action recognition. I will also discuss these methods with its references in the following slides. Now, let's start with the single-stream network. Despite there being some papers using convolutional neural network for video action recognition, handcrafted features, particularly improved dense trajectories, dominated video understanding domain until year 2015, due to their high accuracy and good robustness. However, handcrafted features have heavy computational costs which are hard to scale and deploy. Inspired by the success of using deep learning for image classification and object detection, researchers start to exploit for video-related tasks as well. Deep video is a seminal work of using a single 2D CNN model on each video frames independently and investigated several temporal connected patterns to learn spatial temporal features for video action recognition. The model contains a multi-resolution network, as can be seen in the figure, including a foveal stream and a context stream, where the foveal stream aims at a center area and the context stream focuses on the entire image. Despite it looks like a two-stream network, it is not the popular two-stream models we talk about, because the two streams here is for multi-resolution, not for motion modeling. Furthermore, researchers found that deep video's performance on UCF 101, which is the most popular dataset back then, was 20% less accurate than handcrafted ITT features. This encouraged people to think about why the CNN hammer did not outperform traditional handcrafted features in the video domain, unlike in other computer vision tasks. One possible reason people tend to believe is that a single-stream CNN lacks the capability of motion modeling. Simply speaking, local convolution operations do not capture motion well. Since video understanding intuitively needs motion information, finding an appropriate way to describe the temporal relationship between frames is essential to improve the performance of CNN-based video action recognition. There are many ways to describe motion, such as using optical flow, using motion vectors, using 3D convolutions, using temporal convolutions, etc. Here, I will first discuss two-stream networks who relies on optical flow. Then I will talk about 3D CNNs-based methods. In the end, I will also include other temporal modeling methods. Okay, so now first two-stream networks. Optical flow is an effective motion representation to describe object scene movement and has been shown to work well on video problems. The traditional handcrafted feature IDT also contains optical flow derived features, such as histogram of optical flow, HOF, and motion boundary histogram, MBH. Hence, Simoian proposed two-stream networks, which included a spatial stream and a temporal stream, as can be seen in this figure. The spatial stream takes raw video frames as input to capture visual appearance information. The temporal stream takes a stack of optical flow images as input to capture motion information between the video frames. By adding the extra temporal stream, for the first time, CAN-based approach achieved similar performance with the previous best handcrafted features IDT on UCF 101 dataset. It significantly outperformed previous deep video approach. This clearly showed that motion information is important for video action recognition. Here, I want to emphasize that a two-stream network is a generic framework for video understanding, instead of a specific network. As long as there are two networks, one is for spatial appearance modeling, the other is for temporal motion modeling, the method could be categorized into the family of two-stream networks. Since two-stream networks manage to close the gap between deep learning approaches and traditional handcrafted features, many follow-up papers emerged and greatly advanced the development of video action recognition using deep learning. Here, I only talk about several of them. Inspired by the good performance of trajectory-based methods, TDD was proposed to conduct a trajectory-constrained pooling to aggregate deep convolutional features into effective descriptors. This new video representation shares the merits of both handcrafted features and deep learned features, and became one of the top performers on both UCF 101 and HMDB 51 datasets in year 2015. Since a video is essentially a temporal sequence, researchers also explored the recurrent neural network RNN for long-range temporal modeling inside a video, particularly the usage of long short-term memory network. Beyond short snippets is one of the first several papers that use LSTM for video action recognition. It takes the feature map from CNNs as an input to a deep LSTM network and aggregate frame-level CNN features into video-level predictions. However, the improvement from using LSTM is not obvious. It only improved a bit over the basic two-stream method, about 0.6% accuracy. Given there are two streams in a two-stream network, there will be a stage that needs to be merged the results from both networks to obtain the final prediction. The earliest and most straightforward way is late fusion, which performs a weighted average of predictions from both streams. Two-stream fusion claims that this may not be the optimal way to fuse information between the spatial appearance stream and the temporal motion stream. It believes that earlier interaction between the two networks could benefit both streams during model learning, and this is termed as early fusion. Motivated by the two-stream network's inability to model long-range temporal structure, Temporal Segment Network (TSN) was proposed to perform video-level action recognition. This framework is simple and effective. Thus, until today, many 2D CNN-based methods are still built upon this framework. To be specific, TSN first divides a whole video into several segments, where the segments distribute uniformly along the temporal dimension. Then, a segmental consensus is performed to aggregate information from the sampled short video clips. In this sense, TSN is capable of modeling long-range temporal structure over the entire video. Moreover, this sparse sampling strategy lowers the training cost over long video sequences, but preserves relevant information. It also achieves a good performance of 94% accuracy on UCF 101 dataset. Following TSN, since the segmental consensus is simply doing a max or average pooling operation, a feature encoding step might generate a global video feature and lead to improved performance as suggested in traditional approaches. So, temporal linear encoding (TLE) network was proposed to embed an encoding layer in the network, such as using Fisher vector encoding, VLAD encoding, or bilinear encoding, to obtain enhanced video level features, while the network is still end-to-end learnable. At this point, which is early year 2017, the performance on UCF 101 dataset has reached 95.6%, achieved by TLE, which is kind of saturating the dataset. So people start to look back and see if there are drawbacks of existing two-stream networks and how to address it. Ironically, one of the biggest problems of two-stream networks is the usage of optical flow. Pre-computing optical flow is computationally intensive and storage demanding, which is not friendly for large-scale training or real-time deployment. For example, the pre-computed optical flow images from Kinetics 400 dataset take several terabytes disk space, which slows down I/O during training. Besides, the flow computation itself is also slow, which limits its use in real-world applications because most video tasks require real time. So there are several new methods emerging, such as 3D CNNs and the recent efficient models without using optical flow. Let's first talk about 3D CNNs. There is an early work of using 3D CNN for video action recognition in the year 2011, inspiring but not deep enough. It does not have enough data at that time to show the potential of 3D CNNs. Hence, Train extended to a deeper 3D network called C3D in the year 2015. C3D follows a modular design of VGG network, just replacing the 2D convolutional kernels with 3D kernels, which could be thought of as a 3D version of VGG16 network. You can see its framework diagram in the figure above. C3D shows strong generalization capability and can be used as a generic feature extractor for various video tasks. But its performance on standard benchmark like UCF 101 is not satisfactory. It is lower than ITT as well as two-stream networks. One possible reason people tend to believe is that 3D networks are hard to optimize. Hence, after 2 years, i3D was proposed to address this problem. The two major contributions from i3D is inflating and bootstrapping. Inflating means it adapts successful 2D image classification architectures instead of designing new 3D architectures. Bootstrapping means it can initialize 3D model weights by porting ImageNet pre-trained 2D model weights. In this way, i3D bypasses a dilemma that 3D CN have to be trained from scratch. With pre-training on a new large-scale dataset, Kinetics 400, i3D achieved 95.6% on UCF 101 using only RGB frames. By using optical flow, two-stream i3D achieved astonishing 98% accuracy on UCF 101, which finally saturates the dataset. i3D ended the era where different methods reported numbers on small-size datasets, such as UCF 101 and HMDB 51. Publications afterwards need to report their performance on Kinetics 400 or other large-scale benchmark datasets, like Sports 1 Meeting or Moment in Time. And this took video action recognition to the next level we are at right now. In the next few years, 3D CNNs advanced quickly, and it became top performers on almost every benchmark dataset. Here, I only talk about several of them, like P3D, Eco, non-local, slow-fast, and X3D. To reduce the complexity of 3D network training, P3D explores the idea of 3D factorization. To be specific, a 3D kernel, for example 3 by 3 by 3, can be factorized into two separate operations, a 2D spatial convolution, for example 1 by 3 by 3, and a 1D temporal convolution, for example 3 by 1 by 1. A concurrent work termed R2 plus 1D also adopts this kind of factorization, but arrange the residual blocks differently. As I mentioned, after i3D, publications need to be compete on large-scale datasets, so I report performance on Kinetics 400 instead of UCF 101. Another way of simplifying 3D CNNs is to mix 2D and 3D convolutions in a single network, such as MICTNet, ArtNet, S3D, and Eco. Here we use Eco as an illustration. Eco replaces the 3D convolution at the bottom of the network with 2D kernels, and find that this kind of top-heavy network has both higher accuracy and efficiency. In 3D CNNs, long-range temporal connection may be achieved by stacking multiple short temporal convolutions. However, Useful temporal information may be lost in the later stages of a deep network, especially for frames far apart. In order to perform long-range temporal modeling, non-local module was proposed to capture the long-range dependencies in both space and temporal domain. It is a generic operation similar to self-attention and achieved improved performance over baselines without bells and whistles. In order to further improve the efficiency of 3D CNNs, for example in terms of flops, model parameters, and latency, slow-fast was proposed with a slow pathway and a fast pathway. The network design is partially inspired by the biological P and M cells in the primate visual system. The slow pathway operates at low frame rates to capture detailed semantic information, while the fast pathway operates at high temporal resolution to capture rapidly changing motion. Although slow-fast has two pathways, it is different from the two-stream networks, because the two pathways are designed to model different temporal speeds, not spatial and temporal modeling. Following this line, X3D was proposed very recently at this year's CVPR. It progressively expanded 2D image classification architecture along multiple network axes, such as temporal duration, frame rate, spatial resolution, width, bottleneck width, and depth. X3D pushes a 3D model modification and factorization to an extreme. It is a family of efficient video networks to meet different requirements of target complexity. X3D is a good summarization of recent 3D CNN methods. I highly recommend to read it. And it achieves a promising performance of 80.4% on Kinetic 400 dataset, which is a state of art of right now. Now, let's talk about some other motion modeling methods other than the optical flow and the 3D CNs. I list several papers or directions here, like rank pooling, compressed videos, hidden two-stream networks, trajectory conv, relationship, temporal shift module, and temporal excitation and aggregation. But of course, this is not a complete list. Rank pooling, also known as learning to rank, starts from a CVPR 2015 work, Video Darwin. It uses a ranking machine to learn the evolution of appearance over time and return a ranking function. The ranking function should be able to order the frames of a video temporally. Thus, we can use a parameter of this ranking machine as a new video representation. The first version, Video Darwin, is not a deep learning method, but there were several follow-up work making ranking pooling as a differentiable layer. This idea also demonstrates the usefulness of temporal order, which inspires later self-supervised video representation learning methods, such as shuffle and learn. Most video action recognition approaches use raw videos, or like decoded video frames as input. However, there were several drawbacks of using raw videos, such as a huge amount of data and high temporal redundancy. Video compression methods usually store one frame by reusing content from another's frame. The another frame is an iframe, and we only store the difference, like the p frame, because of the fact that adjacent frames are similar. Here, the iframe is the original RGB frame, and the p frames include the motion vector and the residue, which are used to store the differences. Motivated by the development in video compression domain, researchers start to adopt compressed video representations as input to train effective video models. Cover here is a recent work using a high-weight CNN for the iframe and a lightweight CNN for the p frames. This approach requires that the motion vector and the residue for each p frame can be referred back to the iframe by accumulation. There are also some other work trying to use enhanced motion vector to replace optical flow to speed up the network inference. Instead of replacing optical flow, hidden two-stream network completely remove the need of optical flow by proposing MotionNet. MotionNet is a lightweight network to learn motion information in an unsupervised manner, and when concatenated with a temporal stream, is end-to-end trainable. So hidden two-stream CNNs only takes raw video frames as input and directly predict action classes without explicitly computing optical flow, regardless of whether it's in the training or inference stage. Following the direction, several other flow work continue to investigate end-to-end trainable CNNs to learn optical flow-like features from data, like OFF representation flow. They derive such features directly from the definition of optical flow. Following hidden two-stream networks and trajectory pooling (TDD), trajectory convolution was proposed to learn motion-enhanced features in an end-to-end network. Its goal is to replace standard temporal convolution with trajectory-based convolution. This method is generalizable to action localization and other video tasks as well. It again shows that we can achieve more if we can combine the best of both worlds, deep learning and traditional computer vision methods. Another new direction of motion modeling is called relationship. Because temporal relational reasoning, the ability to link meaningful transformation of objects or entity over time, is a fundamental property of intelligent species. In the TRN paper, the authors introduce an effective and interpretable network module, the TR Temporal Relationship Network. It is designed to learn and reason about temporal dependencies between video frames at multiple time scales. Recent work Temporal Pyramid Network, TPN, also followed this line of research and achieved SoTA on kinetics dataset. Lin recently introduced a new method termed Temporal Shift Module, TSM. TSM extends the shift operation to video understanding. It shifts part of the channels along the temporal dimension, thus facilitating information exchanged among neighboring frames. It can be inserted into a 2D CNN to achieve temporal modeling at zero computational cost and zero parameters. Since this method is 2D method, all the distributed training methods can be directly applied. So using TSM, the authors show that they can train TSM network on Kinetic 400 dataset in 15 minutes on a large-scale cluster. Besides, the method can also be used for video object detection. There are several other 2D CNS approaches using attention to perform long-term temporal modeling, such as STM, TenNet, and TEA. They all have a channel-wise spatial temporal module to present spatial temporal features and a channel-wise motion module to efficiently encode motion features. Here we talk about TEA. Inspired by SENet, TEA uses motion features to recalibrate the spatial temporal features to enhance the motion pattern, and which is accepted as this year's CVPR 2020. Okay, so now let's look at this timeline again to see what we have covered. Maybe this will give you a better and deeper understanding of recent progress on video modeling. So, starting from the deep video in year 2014, researchers proposed to use different motion modeling methods to improve deep learning-based video action recognition. During year 2014 to 2017, two-stream networks dominated the research field due to its simplicity and good performance. With more computing resources and larger datasets, researchers' focus started to shift from 2D CNNs to 3D CNNs. From the year 2017 to now, 3D CNNs develop quickly and achieve great performance. However, both two-stream networks and 3D CNNs are computationally expensive and hard to deploy. So recently, people started looking to efficient modeling. For example, without using optical flow, we're using a combination of 2D and 3D convolutions in a single network. I believe in the near future, this will still be the trend. Researchers propose using new ways to efficiently model motion or temporal relationship in a video, either by shifting or attention or neural architecture search. Now I will present the second half of my talk, which is an introduction to GluonCV video model zoo. First, let me show you the model zoo of GluonCV video toolkit. Due to space limit, we only show the models trained on Kinetics 400 datasets, and we host more in the web page shown above. We have coverage for TSM models with various backbones like Inception V1, Inception V3, and all ResNest. We also have C3D, P3D, R2+1D, I3D, non-local, slow-fast models. All the models have comparable or better performance than it reported in the original paper. We also provide training command and training logs, which makes all the models in our model zoo fully reproducible. In addition, we're actively maintaining the toolkit and adding more models to it, such as TSM, Temporal Shift Module, TVN, Tiny Video Networks, TPN, Temporal Pyramid Networks, and the TEA, Temporal Excitation and Aggregation Method. Pull requests are on the way. Please stay tuned. In terms of dataset, we provide support for most popular video action recognition datasets, including UCF101, HMDB51, something something V1 and V2, and Kinetics 400. And more dataset support will be in the next release, including HAX, Kinetics 600, Kinetics 700, and Moments in Time dataset. We want to make GluonCV Video Toolkit a go-to place for video-related tasks, for both students, researchers, and engineers. Please leave issues, request features, and contributions is always welcomed. Next, in order to address the problem of slowness in deep video training, we introduce a new efficient video reader called chord. Chord provides easy-to-use Python interface for video slicing and high efficiency over existing video readers. You can see this in the figure. Chord is faster than both OpenCV and PyAV, especially on accurate random seek, we are 14 times faster than OpenCV. In the case that we care most, which is a real-world training case, we are 6 times faster than OpenCV and 2 times faster than PyAV. Besides, chord supports both CPU and GPU video loading. It also supports multiple platforms, including Windows, Linux, and Mac. It supports reading video either online or offline, and it provides bridges to multiple deep learning frameworks, including MXNet, PyTorch, and TensorFlow. I will talk about more details on chord in the next talk. With all these models and datasets, you need tutorials. At GluonCV, we provide extensive tutorials to help you get started. We have step-by-step instructions on how to prepare datasets, and we provide a single Python file to download and preprocess the datasets for you. We also have tutorials on how to perform inference on a single video or a list of videos, how to reproduce data-forward method, how to fine-tune video classification models on your datasets, and how to perform feature extraction, and how to do distributed training. Now, let's see another advantage of GluonCV Video Toolkit. Its flexible and customized usage. We provide a generic video loader, video classification custom, for users to load their data. All you need to prepare is just a text file, specifying where your video store. Like in the example below, you provide a train.txt file and specify the config how you want to read the videos. Our data loader will handle the rest for you. You don't need to write a single line of code. Besides, your videos can be stored in any hierarchy. You just need to put a process in the text file. Our generic data loader supports both frame loading and video loading. At this time, we use this loader to load all the datasets in GluonCV, like UCF101, something something, and Kinetics 400 dataset. We also plan to make it more powerful by using the same loader for all video-related tasks, including multi-label video classification, tracking, and action localization problems. So take a quick example. When you do inference, or training, or fine-tuning, or feature extraction, you only need to prepare a text file like this, with the first item being video path, second item being the length of the video, and the third item is the label of the video. That's it. Actually, if you use Video Loader, you don't need to get the actual length of the video, because our video reader will know it on the fly during training. You don't need to worry about the complicated data preprocessing anymore. We also provide customized usage for models. We provide several off-the-shelf customized popular models for users to train and fine-tune on their own data. For example, C2D, I3D, and SlowFast. Users can just call the customized models and tell how many classes are there will be fine. You can also specify using connected pre-trained weights or not, and freeze the backbone or not of the network by simply configuring it. Again, no coding is required. In addition, GluonCV supports you no matter you have more computing resources or less. Natively, we support multi-GPU training using data parallel. If you have more resources, we support multi-machine distributed training. We can have 6 times speed up using 8 machines with 0.75 scaling ratio. But if you have less resources like only one GPU, you can also train large models like i3D or SlowFast with gradient accumulation. There is no performance degradation. Besides faster training and comprehensive video model zoo, the best part of using GluonCV and MXNet is its conveniency for deployment. For CPUs, we continue to collaborate closely with Intel on adding more Int8 models in GluonCV. As you can see, using Int8 models can have the same performance with FP32 models, but around 5 times faster. For other hardware like edge devices, we also provide seamlessly support from TVM to deploy video models. More details about deployment using TVM will be in our next talk, Deploy Video Models. In the end, I want to talk about some observations or experience I had during reproducing all these experiments. First, I want to talk about the classification head, which is the last layer of all the models. It is usually a FC layer, with output dimension being the number of classes. Particularly, it has a parameter standard deviation when you initialize this layer. Actually, I didn't put my attention on this parameter until I couldn't reproduce TSN experiments on UCF 101 because I used the default value 0.01. As you can see in this table, the standard deviation value during model initialization has a big impact on the final performance. In the case of TSN, it has almost a 2% gap between using different values of STD. In my observation, a small value of STD should be used for small-scale datasets, particularly during fine-tuning, and a big value is preferred for large-scale datasets with more classes, especially when training from scratch. Another observation is, for 3D scenes, the number of frames used in a clip matter to the final performance. For example, if you use 8 frames to train an S3D model with a ResNet 50 backbone, the best performance is achieved when you use 8 frames to test the model as well. If you change the number of frames during training and testing, the performance will vary. The worst performance is obtained when you use 32 frames to train the model and only use 8 frames to test it. The performance drops about 2%. So this is also a problem in current video modeling, the fair comparison problem. Some papers report performance using 8 frames, some use 32, and some people use 32 frames from a 64-frame clip. These are all important factors that can contribute to the final performance. As we mentioned above, the advantage of i3D is it bypasses the training from scratch and achieves good performance. But now, some recent methods trained from scratch is fine and didn't notice any performance degradation, such as SlowFast. So, do we really need 2D ImageNet pre-trained weights as model initialization for 3D CNNs? In our reproducing experiments, we find that not necessary, at least for most 3D CNNs using RGB input alone, like C3D, P3D, R2 plus 1D, I3D, S3D, and SlowFast. We don't need to initialize 3D CNNs from 2D weights. We can just train from scratch. This is good news because in this case, we can develop new 3D architectures without constraining ourselves to existing 2D architectures. We can also do video neural architecture search. To summarize, video understanding is the next battlefield. More and more focus has been put on video-related research. There are also many potential directions to work on, such as video domain adaptation, efficient video models, self-supervised video representation learning, video adversarial attack, fine-grained video classification, and multimodality learning. It is just an exciting field. In order to get started, we hope you find the GluonCV Video Toolkit is useful. Welcome to leave issues, require features, and make contributions at gluoncv-cv.mxnet.io. Also, please stay tuned. We have a survey paper coming, which is about using deep learning for video action recognition. We have reviewed 200 plus papers and provide comparisons in terms of both accuracy and speed. In the end, all the pre-recorded videos, slides, and the survey paper will be uploaded to the tutorial website. Thank you.